In this video, we're going to continue discussing energy and specifically define what we mean by work. In our previous video, we said that if an object has energy, it has the ability to do work, and therefore we need to define the concept. Here's the physics definition of work. Work is defined to be the product of the magnitude of the displacement times the component of the force parallel to the displacement. So let's take a look at our picture here. Let's say that our person drags this box over to this position. So in other words, the displacement, which we're going to use delta R for general displacement, the displacement delta R is to the right. Notice that our person is exerting a force at some angle with respect to the displacement. So what is the component of the force in the direction of motion? Well, it would be this component here, which you can see is F cosine theta. So if we take delta R and multiply it by F cosine theta, that's our definition of work. In general, when we actually write it, we write it this way, that it's the force times the displacement times the cosine of the angle. And that is the angle between F and delta R. Based on our definition of work, that work is F delta R cosine theta, what are the units of work? Well, we can see looking at the formula that the units of force are newtons, the units of displacement are meters. So one answer would be newtons times meters. However, we also know from Newton's second law that a newton is a kilogram meter per second squared. So we have that times meters, or a kilogram meters squared per second squared. So newtons times meters, or kilogram meters squared per second squared. Now, because work and energy are such important concepts, we define a new unit, and we define the unit of the joule. So 1 joule is 1 kilogram meters squared per second squared. So when we do work on an object, what does it mean when we do work? This is the key phrase I want you to memorize. When we do work on an object, we give it energy or take energy away. So that's what we mean when we say a force does work on an object, like our person dragging that box. Well, they were either giving the object energy or taking it away. If the work is positive, they're giving it energy, as in the case of dragging that box. We'll see that some forces do negative work, like friction. Force and displacement are vectors. What do you think work is? And remember, work is just the amount of energy you give an object or take away when you exert a force on it. So what do you think? Is work a vector or a scalar? Well, you probably can guess that energy and work are scalars. And if you think about that, when you go and you buy energy, for example, you buy gasoline, you have to say an amount that you want. I want 10 gallons of gasoline. But you don't say I need 10 gallons of gasoline to the right. In other words, when you specify an amount of energy, you don't have to give both a magnitude and a direction. So energy is a scalar. And by the way, that's a real key for why it is that using energy is useful in problem solving, because it's always easier to work with scalars than it is with vectors. Let's do a simple problem here to get us started. A man pulls a child on a sled with a force of 10 newtons at an angle of 30 degrees for a horizontal distance of 5 meters. How much work is done on the sled? Why don't you go ahead and pause the video and calculate that yourself. Okay, so we're just going to apply our formula that the work is equal to F delta R cosine theta. And in this particular case, we've got a force of 10 newtons. We've got a displacement of 5 meters. And the angle between the force that's being applied and the displacement of the object is 30 degrees. When you calculate that, you should have gotten 43 joules. By the way, remember that in this case we're working in degrees, so make sure that your calculator is in degree mode. Now, where does that energy go? In our last video, we talked about the fact that energy can be transformed from one type to another, and it can be also transferred from one object to another. So our person is doing work on this sled. They are transferring energy to the sled. Well, what form does that energy end up in? Well, definitely at least some of it ends up in kinetic energy. In other words, the sled is now moving, which it wasn't before. So that means it now has kinetic energy, which it didn't have before. Unless we have a perfectly frictionless surface here, then also some of the energy is being lost to friction. And if you take your hands together and rub them, feeling that friction between your hands, you'll notice they get warm. So ultimately, whenever there's friction present in a problem, some energy is turning into thermal energy. And so that 43 joules of work that the person does on the sled goes into both kinetic energy of the sled and thermal energy. Let's talk a little bit more about this idea of vectors and scalars. When we covered vectors earlier in the course, we talked about how to add vectors, subtract vectors. We talked about how to multiply a vector by a scalar. But you'll notice what we haven't talked about yet is what happens when you multiply vectors together. It turns out there are two different ways to do that. We're going to talk about the first one here, which is called the scalar or dot product. And we call it the dot product because we use a big dot to denote it. But the scalar product, scalar is probably a better term because the scalar product tells you exactly what's happening. It's the way that we take two vectors, multiply them, and end up with a scalar. Later on in the course, we'll talk about the vector or cross product. Okay, so it turns out there are two different ways to calculate the scalar product. If you have the magnitudes of each of the vectors, so this is vector A and vector B, where A and B are the magnitudes. Remember that the magnitudes of a vector are always positive. It's just the length of the vector. And what theta represents is the angle between A and B. So for example, let's say vector A is in this direction and vector B is in this direction. That's theta. It's the angle between A and B. So it's not the angle with respect to the positive x-axis. Obviously, if one of the vectors is in the direction of the x-axis, it is. But in general, it's the angle between the two vectors. So if we want to calculate the scalar product, we simply need the lengths or magnitudes of the two vectors and the angle between them, and we can calculate it. Now, if we have our vectors in unit vector notation, so in other words, instead of having the magnitudes of the vectors and their direction relative to each other, maybe I know that vector A is made up of an x component, a y component, and a z component, and I have it in unit vector notation like that. And let's say that I also have that information for vector B. Well, in that case, if I want to calculate the dot product or scalar product of those two vectors, you'll notice that what I do is I just take the x components and multiply them, the y components and multiply them, and the z components and multiply them, and then just add it all up. Notice that there are no i's, j's, or k's here because, remember, it's a scalar product. We should end up with just a number. No direction is there. Okay, so how does this relate to work? Well, what we now can understand is that work is actually the scalar product of the force and the displacement. Well, remember, we've got two ways to calculate the scalar or dot product. And so the way that we do it just depends on what information we have. So if we have the magnitude of the force being applied, and we have the magnitude of the displacement, and we have the angle between them, then we use F delta R cosine theta as we've already introduced. On the other hand, if instead we have the force and the displacement vectors, then we use our second definition. Now, by the way, let me talk a little bit about our vector delta R. Remember, delta R represents the displacement. Well, most generally, we could have a three-dimensional displacement, one that we've gone in both the x, the y, and the z direction. And so here's how we would write that out. Delta x would be how far we go in the x, delta y in the y, and delta z in the z direction. So if we've got the force in unit vector notation and the displacement in unit vector notation, then we calculate the work using our second method of calculating the dot or scalar product. So let's go ahead and try this out. You might want to, in fact, I'd like you to pause the video and try this on your own. Be very careful about reading the problem carefully. A force F equals 2.3 I minus 4.7 K newtons acts on a particle that undergoes a displacement, delta R, is equal to 3.0 I plus 1.0 J meters. What's the work done by the force on the particle? So go ahead and try it out on your own. Okay, well, in this problem, we can see we've got our force and our displacement written as vectors. And so we definitely want to use this method of finding the scalar product. So we've got our x components, our y components, and our z components. Now, the reason I mentioned reading the problem carefully here is you'll notice that the force only has an x and a z component. And the displacement only has an x and a y component. So we've got to pay attention to that ijk. Remember, ijk is x, y, z. So the x component of the force is 2.3. The x component of the displacement is 3. The y component of the force is 0. There is no j component. The y component of the displacement is 1. And then the z component of the force is negative 4.7. But there is no z component of the displacement. And now I simply have to do the math. You'll notice only that first term results in any value. And what we get is that the work is 6.9 joules. Notice again, no i's, j's, or k's in that answer because it's a scalar. Make sure that you remember that. The i's, j's, and k's don't end up in the answer because it's just got to be a magnitude. Now, conceptually, thinking about when we do work on an object. I've mentioned before that when we do work on an object, we can either be giving the object energy or taking it away. Well, if we look at our formula, we can see what range of angles is responsible for giving the object energy or taking it away. If theta is greater than negative 90 or less than 90 degrees, then we know that the cosine of theta is going to be greater than 0 and less than or equal to 1. And therefore, when that angle is between negative 90 and 90, we know that we're doing positive work. So in other words, at least part of the force is acting in the same direction as the displacement. That's when we get positive work. You'll notice that whether the force is, as I've drawn it here, or whether that force has a negative angle, in both of those cases, we'd be doing positive work. And again, what does that mean? It means that that force exerted through a displacement is giving the object energy. The object ends up with more energy than it started with. Now, what happens if theta is 90 or negative 90? Well, in that case, we know that the cosine of theta is 0. So if the force is at right angles to the displacement, then it does no work. So think about this. Notice that the normal force does no work. And that makes sense. Just because an object is sliding along a surface, it's not like the surface is giving the object energy or taking energy away from the object. So it makes sense that the normal force doesn't do any work. Notice also in the case of an object on a flat surface, gravity doesn't do any work either, because it's at 90 degrees to the displacement. However, if we think about an object on an incline, notice that for that object, the normal force still doesn't do work because it's perpendicular to the displacement delta r. However, the force of gravity now does do work. And that's, from an energy perspective, why that block would slide down the incline, because gravity does positive work on the object. Now, what about when the force acts at least partly opposite the direction of the displacement? Well, in that case, the work done is negative. So in other words, when theta is greater than 90 or less than 270 degrees, what we know is that the cosine of theta is greater than or equal to negative 1 and less than 0. Therefore, we can see that the work is going to be negative. So if our object here is moving to the right and the force at least is somewhat to the left, then the work done is negative. We're taking energy away from the object. Let's look at a key example, which is friction. Remember that friction always acts directly opposite the direction of motion. So if I've got a block that has a displacement to the right, we know that the force of friction is to the left. And so notice that that angle is always 180 degrees for friction. That's important. Always 180 degrees. And therefore, friction is taking away the maximum amount of energy, because we know that when theta is 180 degrees, the cosine of theta is equal to negative 1. So always for friction. And again, that makes sense. Friction is never helping you. If you're trying to slide a heavy box along the floor, you never say to yourself, gosh, I'm glad there's friction. This is really making my life easier, right? It's the opposite. It's making your life harder, because it's taking away energy, which means that for you to move the box, you've got to be putting in more energy than if there were no friction. Let's end up this video with a couple conceptual questions. So go ahead and pause the video after we read the question and see if you can get the correct answer. I hold a 10-kilogram bag of groceries 2 meters above the floor for 23 seconds. How much work do I do on the bag? Okay, well, let's see how you did. We know that work is equal to F delta R cosine theta. Here's the key thing about work. It's not enough to have to exert a force. You have to exert the force through a displacement. And in this case, you'll notice the bag of groceries is not moving. We're just holding it. Now, it might feel like you're doing work because your muscles are working to hold that bag up. But remember, what we mean by work is, are we giving the object energy or taking energy away? If all you're doing is keeping that bag stationary, you're certainly not giving it any energy or taking energy away. And that's because the displacement, delta r, is 0. So yes, you're exerting a force, but you're not exerting it through a displacement, and therefore you are doing no work on the bag. Now, if you lift up the bag from the ground and lift it up to a height, now you're exerting a force through a displacement. Now you would have done work on the object. One last conceptual question. The work done by friction is. Go ahead, pause the video and think about it. All right, hopefully you got this one right. It's always negative. Friction never helps you out. Again, when we calculate the work done by friction, what we know is that the force of friction is always directly opposite the direction of motion. So Fk and delta r are always opposite. And therefore, again, theta is always 180 degrees for friction. By the way, one last quick note that's really important to remember. When you calculate the work done by a force through a distance, remember, these numbers are always positive. Because what do we mean by those? Those are the magnitudes. So don't think about, don't put in a negative value for friction. You got to put in the positive value. Where the negative sign comes out of is from here, is from the angle between the force and the displacement. In our next video, we'll look at how we can use this concept of work to derive the concept of kinetic energy.